All right. Hey everybody, I'm Steve. Thanks for coming to my talk. This talk is titled "Should We Have a 2021 Edition?" And today is the 27th. For those of you who don't know, I am on the core team of Rust. I previously led the documentation team, and I wrote the Rust programming language, which is the introductory book on Rust that comes with Rust itself. Two other things, though, that you may or may not know, I figured I would mention before I get into the meat of this talk. I recently got a new job at a company called Oxide Computer Company. We're building new server computers for people to use, and we're doing like everything in Rust. So these days I'm like writing embedded Rust, and it's awesome. And we've had an embedded working group working on it for a while, and I appreciated their work in the abstract sense, but now that I'm actually doing their work as my job, it's fantastic. So that's pretty cool. And we are also hiring. So if you are interested in a job where you will write a lot of Rust, you may want to check that out. Finally, I've started actually working on open source Rust streaming stuff. So I'm doing my Twitch now. So if you want to watch me program on Tuesdays, that's the thing I'm doing. Okay, anyway, enough about me. You want to hear about additions. So today we're going to kind of cover these like three major points in this order. So the first one is, what exactly are additions? I want to make sure that we're on the same page about the details, because the details do actually matter and matter a lot here. Secondly, we've already done sort of one edition release, which is Rust 2018. And so I kind of want to take a look at that and like kind of how it went and some like thoughts, after some time has passed. So it's kind of like a little bit of a case study, maybe a little bit of retrospective, but let's like talk about Rust 2018. And then finally, like, what should we actually do? And this is phrased as, should we have Rust 2021? Then that's kind of like a big thing people have been talking about lately. I want to sort of emphasize, especially with both of these second sections, that this is like my personal opinion. While I am on the core team, I am only one person, and this is all phrased as like should we, because technically nothing has been decided. So while I do have my own opinions on this, feel free to disagree, and just like this is me saying this. So take that as far as that goes. All right, so first up, this first section, what even are additions anyway? If you don't know at all, thank you for coming to my talk, even though you don't know the subject. This is exactly why I included this section. But even if you do, there's some details that maybe some people don't always think about. So I want to talk about a lot of those details. There's kind of two aspects to additions that I think are really important. And the first one is the sort of social aspect of Rust. So an addition is kind of this point in time where we say, hey, Rust is significantly different now than it was in the past, and here's kind of like why. So Rust 1.0 came out in 2015. Rust 2018 was the first edition sort of release, and it came out in 2018. And we sort of said like, hey, Rust has changed a lot in the last 3 years. Let's talk about all the stuff we've accomplished and add in some other things. And so that's like largely a social thing. So this is a way to sort of reflect on the longer term progress of the language and the project as a whole. Because we release every 6 weeks, that is like a really great thing for a lot of reasons, but it's really hard to like remember how much work we've done. Releases come out all the time, and they're in small little chunks, and so it can be really, really easy to forget like just how far along things came. Half the time I forget that it's been like almost 5 years since Rust 1.0, because when things are happening at such a rapid pace, it's really easy to lose track of like how far we've come. And so that's like really important. A second one is a point on like why additions matter, are that they're a way to get new users into Rust. So this sort of is kind of similar to the first point, but a little bit different. Basically, because we release every 6 weeks, there's a lot of people who don't pay attention to Rust releases because they see them so often and they have not that much in them. And so they're kind of like, hey, a new Rust release happens, I don't care. With languages that release like once a year or once every couple of years, it's a really big deal. And so a lot of people will like hear about like, oh, there's a new version of C++ out, or there's a new version of Ruby out, or the new C# has these cool new things in it. And that's a way for people who don't currently program in the language to sort of like it signals to them, hey, I should check this out. Maybe, I looked at C# 3.0 and I didn't really like what was going on, so I didn't use it. Maybe C# 4, like time for me to check in again. Maybe I want to start programming in it. And so it's kind of a nice way to signal to people outside of the Rust world as well, that, hey, a lot has gone on, and maybe if you didn't use Rust in the past, you would want to use it again. And then finally, like kind of for actually like development of Rust, sort of like a nice like rallying cry, I guess, basically. Like, not only is it about reflecting on what we've done, but also if there's sort of big things we want to do, it's nice to be able to point in the near future and say like, hey, it's 2020 now, we want to do a Rust 2021 and we want to like get people excited. So let's start working on some projects that will like really generate that excitement. And there's some like back and forth here, and we're going to talk about all those details in a minute, but it can be a really great way to sort of get everybody excited about the future of Rust, because we like need those check-in kind of points, I think. But also additions are not purely a social mechanism, they're also a technical mechanism, and this really matters. And so on a technical level, additions are a way to kind of make breaking changes to the Rust language without actually making breaking changes. And so how this kind of works on a technical level is that additions are opt-in. So you say what addition your code is in, and if you don't update that, then you don't update stuff. So if new things are added in a way that's like technically breaking, then it doesn't break you, because if you didn't opt into the new changes, then your code still works forever. So this is like very different than Python 2 to Python 3, for example, where you can't run your code kind of like together. And similar kind of things like that. So we can like make it a way to opt in to breaking changes, and that's really, really important for compatibility reasons. And then finally, additions are not allowed to change everything about Rust. This is a technical problem as much as it is a social problem, and there's some interplay back and forth between the two. But basically, like major changes are not actually allowed. So some kinds of breaking changes are fine, but there are some kinds of changes that cannot be made in the addition mechanism, and that's due to the technical details of how all of this works. It is also kind of a social thing in the sense that it's also useful for humans. Like if tomorrow, like say Rust 2021 was going to be like garbage collected and use significant white space instead of curly braces, it would effectively be a whole different language. And that would make it a really big challenge for people to update to. But because we can only make certain kinds of breaking changes and additions, it's significantly better for people to be able to upgrade. Not only because of the opt-in nature of things, but also just like Rust is still going to be Rust, even if there are some tweaks to how it works and some changes, like the core idea of Rust will be the same. So let's talk a little bit about what I mean by breaking changes in an addition. So I think one of the best examples of a breaking change was the async keyword. So Rust has, as I said, sort of two editions right now, 2015 and 2018. And in Rust 2015, code is, async is not a keyword, but in 2018 it is. And so what that means is, if you look at this code that I have here on the left, we have a function named async that just takes an integer and returns it. It doesn't do anything fancy, but we call it passing in a 5 and used underscore s as the name, since we never use the variable, to get rid of that kind of warning. So if I run this code on Rust 2815, as you can see, this is the playpen interface on play.rustlang.org. You can choose this little drop down with the 3 dots and then pick which edition you're in. So if you choose Rust 2015, this code will compile and it runs, doesn't do anything because we just pass an integer around, so there's no output. But if we change that to edition 2018, we will get an error, and this will say expected identifier found keyword async. So we're allowed to name a function async in Rust 2015 because it's not a keyword, but we're not allowed to name it in async in Rust 2018 because it is a keyword. So this is an example of, if we purely made this change in the language, code that existed and ran just fine before would end up breaking. So this is like a breaking change. But because you can choose whether or not to upgrade, it's like not a breaking change. And so this kind of like duality, it was a very controversial around coming up with the plan of additions, and it was also one of the big challenges of communicating this to users. Like technically it's breaking, but it's also not breaking, is very interesting and kind of unusual. Oh, is my mic still working? All right, cool. Dropped out there for a second. So the way that you opt into this change, if you're not on the playpen, because most serious Rust programs are not running in the playpen, that would be ridiculous, is in the cargo.toml. So you get to choose an addition mechanism, an addition key by putting 2018 in there. And if this does not exist at all, then it defaults to 2015. So all of the code that was generated before we had this idea of additions, it is able to stay on the sort of the default 2015 edition. But if you opt in, then you're able to do this. And cargo new will start generating 2018. So I just typed cargo new to generate this, and it defaults me to the latest. And so that way we're able to, like, new projects start in the latest edition, but older projects stay on the edition they were created with until their creators explicitly opt in. So that's kind of like the way that this happens in most real projects. And one thing that's really important, though, about additions is that additions can interoperate just fine. So let's say that I had packaged up my useless async function into a crate, and I wanted to use it from some code that was in Rust 2018. Well, one of the features that was added in Rust 2018 was the ability to use a raw keyword. So I showed you the error message in the 2018 code before, but right below the error is a little help message that says, hey, you can escape keywords to use them as identifiers. And so here with this R pound sign, both at the call site and at the actual declaration site, you're able to still define and call a function named async even though it's a keyword. So this would matter if you could imagine that the async function lived in a 2015 crate, then I would still be able to call it from a 2018 crate, and vice versa if there was some other way of doing it. So this is one example of the ways that code can interoperate, but just in general, like, kind of the idea is that you don't have to be worried about your dependencies at all. Other code is allowed to be in any edition, and they'll compile into your project just fine, and there's no like worrying about this kind of interoperability compatibility, other than if some keywords are named a certain way, and then you have to know this escape mechanism. But what this means is we don't have this situation whereby when a new edition comes out, everyone is forced to upgrade all at once, because that doesn't happen. It takes a long time, and there's always some people that are going to sort of prefer older things, and we don't want to like bifurcate the ecosystem. And so this way, these versions can live in total harmony, and your dependencies can upgrade at their leisure, and you can upgrade as fast or as slow as you'd like, and you're not locked out of the rest of Rust world. So that's a really like helpful way to make sure that all of this operates smoothly. And so specifically, I'd mentioned before, part of the way that this works is that additions are not allowed to change everything. So these are the rules that were set out in the original RFC, and they're not complete. So this is not necessarily like a full list of everything that can and can't change, but I wanted to like point out some specifics. So an example of a thing that can change, as I've already showed you, is new keywords. So we're allowed to define new keywords and new additions, and that's totally fine. It's like I said, they interop across the boundary, no problems. The second thing that additions are allowed to change is they're allowed to repurpose existing syntax. And I say repurpose because like you can remove existing syntax. It's like how it gets repurposed, but like it generally shouldn't only remove, it should like replace with something that does something slightly different. So an example of this is if you have the usage of a trait. In this case, I'm just calling it trait. But if you're using this as a trait object, you would just use the name of the trait originally. So you'd have like box trait or arc trait, something like that. And so what we did in the 2018 edition was we sort of deprecated that usage of just trait on its own, and we introduced dyn trait. Unfortunately, my slides kind of split this onto 2 lines. Normally it would be just 1 line, but like this helped you know that, hey, this is a trait object because we're doing dynamic dispatch. And so we kind of like replaced that existing syntax for doing a thing with a new syntax instead. And so you're able to, use this new syntax, and it's like more clear to people that dynamic dispatch is what's happening. So we're allowed to kind of like change some existing stuff and add some new things and like tweak things. Another example of something that changed in the 2018 edition was the module system, which is a pretty big change. I'll talk about all the changes we made a little bit later. But there's also some things that we can't do. Earlier, I mentioned that We couldn't make really big sweeping changes, but like there's actually slightly more specific things. Some of them are based on practical limitations, and some of them are based on decisions that we've made. So for example, the coherence rules can't change across editions. If you're not familiar, a coherence rule says like if a type implements a trait, is it allowed to implement that trait or not? Like, do you get a compiler error when you try to compile a trait implementation for a type? So, a common example of this rule being broken is that if I had, say, a type that's defined in the standard library, like string, and I have a type that's defined in a third-party package, it's not mine, say maybe like serde, I can't define serde serialize for a string because it's not my trait, it's not my type, so that doesn't work. If I had made my own string type, then I'd be allowed to implement serde's trait for it. And if I implemented my own trait, I'd be allowed to implement it on the standard library string, but I have to own either one of the traits or the types. And the rules are a little more complicated than that, but like that's the gist of it. That's the biggest thing. So that's not allowed to change. We couldn't say relax them in one edition, but not in the other. And that's because coherence rules are kind of global, and those rules happen across different crates. So if we had different rules for different parts of your program, that would be extremely hard to implement, very confusing, and possibly just unsound. Like it's not kind of a thing that you're able to do for all of those sort of reasons. So the coherence rules have to act globally, and so therefore they kind of have to stay the same in every edition, no matter what. So that's a trick. Secondly, another thing that people sort of don't always appreciate is that we can't make breaking changes to the standard library. And intuitively, you're like, wait, if I can change crates, standard library is just a crate. Like, why not? Well, I mean, it is just a crate, but it's also kind of not just a crate. You get one copy of the standard library for your whole program. And so if you had a dependency that used Rust 2018 and then you use Rust 2015, say, then you would need both copies. So it doesn't like really work that way exactly. So we're able to sort of deprecate things, but we're not able to remove them. And there's some talk of maybe having some sort of visibility situation where like they exist, but there's visibility rules where this is like only allowed to be seen in 2018 versus 2015. But those are proposals and they're not like real yet. So, this is like kind of half a true technical limitation and half a sort of social limitation. Somebody asked a question on Twitch. How does a deprecated feature move from deprecated to like removed, and can that be done between editions? So one interesting thing about this is that some of this stuff is kind of up in the air policy-wise-ish. Basically, like things cannot actually error on the same edition. So like usually the way you think about it is something becomes a warning in the old edition and then an error in the new edition. And the original RFC talks a little bit about code that's warning free on the first edition should compile. Maybe it'll have new warnings, but it won't break on the second edition. But like if there's warnings in your first edition code, maybe the second edition would break. I'm going to talk a little bit more about this at the end because the exact policy is like a thing that we're talking about. So yeah, the rules are slightly up in the air, but originally that's what the intention was that like you introduce warnings in the first edition, you remove them in the second edition. There's some questions about whether or not that's like too fast or maybe we should like require a whole edition to go by. Like we require language features to wait for a whole release in nightly before we're able to stabilize them, for example. There's kind of a mandatory minimum waiting period. So maybe there would be a good mandatory waiting period for deprecations. Yeah, so I hope that answers enough of your question. Hey, Jared. But I'll talk about it a little more. Okay, so why do we have these restrictions, like on some level? Like I talked a little bit about some of them with like there's one crate everywhere, but let's get into some details. And I think this matters because this also really helps you understand like why certain things are allowed and why certain things aren't allowed. And it's also just kind of fun to talk about the compiler and how it works. So this next section is going to be about editions, I swear, but it's also kind of how the compiler works because I think that's interesting and kind of matters. So Rust is currently, sort of, kinda, there's an asterisk here, I'm going to get to it later, what's called a multi-pass compiler. And so this is like a classic architecture for compilers. If you take a compiler class in your university, this is how they teach you compilers work. A lot of compilers in the world are implemented this way. Basically what happens is there's concept of passes. So you can you take in a source code and then you spit out something. A lot of older compilers are called one-pass compilers because they directly turn the code into the actual like binary code. So if you think about like it used to have to be a lot of older languages required you to define a variable at the start of functions, for example. That was because they had one-pass compilers, and so they needed to omit the stack space for those variables, first. Okay, it seems to be back. Cool. I don't know why that's happening. It's probably something on my end. But anyway, so yeah, so older compilers were one pass. That's also why a lot of them were super fast. It's because they didn't do a lot of this stuff. But over time, we needed things to be more complicated, and so then people developed multi-pass compilers where you would do multiple steps. So you'd iterate over the source code in multiple ways, and that's how it's produced. So in the Rust compiler, it's like multi-pass architecture as it traditionally existed. And is similar to many other compilers. Basically, you have input being source code, and then it kind of goes through each of these steps in turn. So the first one takes the source code, and it creates an AST out of it, which is an abstract syntax tree. And then it takes that AST, and it produces here, which is high-level IR. And then it takes the high-level IR, and it produces mir, which is the mid-level IR. And then it takes the mid-level IR, and it produces LLVM IR. And then LLVM takes that and produces the final binary. So there's a bunch of these steps, and within these steps, there's kind of smaller steps, and all this sort of like happens. We're going to talk about this in a little more detail. So compilers traditionally are kind of produced in this 3 different phases. That's why you have these passes. You do the full pass, and the full pass, and the full pass, all 3 steps. The first one is like a lexical or syntactic analysis. So is your code well formed? This is like grammar rules. So, does the sentence I'm saying follow proper grammar or not? Does your program follow the language's grammar or not? Secondly is semantic analysis, which does this code make sense? So for example, I could say like, this sentence is false. And that sentence is grammatically correct. So it passes lexical or syntactic analysis, but semantically it's very unclear what it means, because if it's true, then it's saying it's false, which means it's false, which means it's not true. So there's some reflexivity there. It's just the first example I could come up with, but like, you could imagine gibberish, for example, that uses all real words. Maybe it's structurally correct, but it doesn't actually make any sense. So semantic analysis makes sure that the thing that you've said is sensical. And then finally, code generation. This does not really have an analog in existing languages. I guess this is the vocal cords turning it into sound, maybe would be the analogy. I'm stretching this a little too far. But once we verify that everything works and makes sense, we actually produce the binary finally out of it. This step in itself has a bunch of different passes. For example, we talk about optimization passes that sort of run and generate code, faster. So that all happens in this kind of stage. But these are kind of the 3 big giant steps. If you've ever wondered how cargo check works, for example, cargo check will run the lexical and syntactic analysis and the semantic analysis, but won't generate any code. So this is an example of how understanding this can help you practically as a Rust developer. If you use cargo check to check your code makes sense, but you don't actually want to run it, you can save yourself a lot of time by not making the compiler do code generation. So this is like one example of how this architecture lets you, do less sometimes. So there's kind of like 2 sorts of these steps between these situations. And this is kind of some compiler jargon that you may be interested in. So one of them is called lowering. And so that's the word that you use when you talk about going from one form to the other. So for example, mir is lowered into LLVMIR, or the AST is lowered into here. And the reason it's called lowering is that at every step along the way, things get simpler. And we throw away things that we've already validated, which makes future steps easier. So for example, mir does not have the concept of complicated fancy loops. So like for loops, for example, don't exist in mir. What happens is the previous steps in the compiler take your for loop and they turn it into a while loop with a break in it. And so mir is able to understand a while loop with a break. So we've sort of removed a construct from the language when we've gotten to the lower step. And that means each successive step is simpler. And this definitely really matters. And that's why it's called lowering, is because you're kind of like breaking down what is happening into simpler and simpler things. And then finally is a step called a pass, which basically means it's some sort of check that validates that your program is well formed and does not necessarily do a transformation, although technically it can. So for example, type checking is a pass on your code. So it runs over your code and it makes sure everything makes sense. A lot of semantic analyses are kind of passes. And sometimes they will do transformations. This is like whenever basically like, okay, I'm going to take your for loop and I'm going to rewrite it as a while loop. That happens first as a pass because inside of here, I believe. And then the lowering step is what turns that simpler form of here into mirror. So they kind of like work together. Okay, so this is some example of actual code going through these steps. And I did this about a year ago. So the samples are a little dated because of the fact that the compiler output changes all the time, but conceptually it's the same. So I figured it being outdated is actually a little better because you shouldn't get hung up on the specifics. So for example, let's talk about taking code and producing an AST. If we have this function called +1, takes 932, adds 1 to it and returns it, we can actually ask the compiler to print out the JSON version of the AST. Because again, these are all data structures inside the compiler, so they don't really have a text representation, but you can like print them out in things like JSON. So for example, +1, a little bit of it looks like this. So there's a statements, and that's an array of nodes. And inside of there, each node has a variance. So this is like an expression. And then, it's like a binary expression that's add. You can kind of see how these little bits all fit together. And then, we're adding X, and it keeps going on to talk about adding 1 and stuff. So you kind of get this data structure view of your code. And that's what Rust's AST looks like. So here, we take our statements, and the statements refers to an expression refers to a binary expression. The binary expression says, hey, we have an add expression that adds X and 1 together. So this is kind of like why it's called a tree, is because if you see there's like this root, which is the statements, and then there's the branches and leaves that happen to build a tree. So this is like what an AST kind of looks like visually. And so, yeah, fundamentally, the AST is a data structure, and it's the way that our code looks written in words, but is a data structure. And this means it's easier to manipulate. Like, if you just have a data structure, you can just manipulate it. Like, that's what they're there for. But if you had to do it on the like textual representation of your code, it would be much harder. So the idea is that we break the text down into a data structure, and then we do all our operations on those data structures. So from the AST, we move on to the here. And so here is short for high level intermediate representation. And this basically is like doing formness sort of checks. And what I mean by formness is like, have you imported all the stuff that you've used? Things like that. And some things are simplified. So for example, in my understanding, here does not have, like use statements. They get turned into the elaborated, like full versions of all the types. So an example of what, kind of like the sort of transformations that happens here, this is a very simple for loop. There's a reason I've referenced for loop several times earlier today, where we take a vector of 5 integers and we loop over it, printing them all out. So the AST would take that literal code as written and represent it that way. But when it gets lowered into here, it ends up being something more like this. So this is like still Rust code that you could write in theory, but you'll notice that the for loop is totally gone, and we now have a loop with a match statement inside, and where we turn the thing that we're iterating over into an iterator, and we call next on it repeatedly until the body of the loop happens and all these things. So you can see how it's kind of like simpler in the sense that there are less language constructs, but it's more complicated in the sense that there's more code. Because like that's the reason we write in the higher level stuff in the first place, is because it's easier to understand for humans. But the computer, having less things makes the analyses much simpler. So we do that kind of stuff. Most checks in the compiler today are done on here, at least in my understanding. So here was the original Rust IR that existed. So the first version of the compiler, or maybe first is a little strong, but like for a very long time, the compiler turned everything into here, and then it went to LLVM IR from there. So it's kind of like the OG thing. So a lot of things are written in terms of here. So two things that are still written in type check or in here are type check, which is like, do all the types make sense, and have you not made any type errors? And then finally method lookup. So that's done at compile time instead of in some dynamic languages. Method lookup is like a dynamic process, but basically, kind of look at like, what trait are you actually calling when you call a method, or is there a trait as an inherent method? Those kind of things. These are all done on here. Then we move from here to mirror. And mirror became the subject of a lot of discussion in the Rust world, so you may have heard about it over the last couple of years. Mirror is ultimately about control flow. So here is kind of represented our code in the way that we wrote it, but mirror totally rewrites it to be in a simpler form, but also one that's based on a control flow graph is the term. rather than an AST, which is the tree. So going from a tree to a graph is helpful for certain kinds of analyses. Specifically, like the graph represents the way that the control goes through your programs, like which statement executes in which order. And that matters because, for example, non-lexical lifetimes, it needs to know how the execution flows within your program to work. And so it was very difficult to write that pass on here. So like this is a practical example of why this stuff matters, is that we had to invent Mir to make non-lexical lifetimes feasible because we needed to be able to encode that flow control to be able to make it actually happen. And I say we because I'm on the team, but like I did none of this work, to be absolutely clear about it. A lot of other really great people made it happen. Man, I don't know what's up with my audio dropping. Anyway, so another interesting thing about Mir beyond the control flow move is that it's kind of the core of Rust. So it's kind of like everything that's rusty about Rust without any superfluous extra concepts. So like I said earlier, fancy loops are gone. Everything is purely loops and breaks. I think it might even have go-tos if I remember correctly. But borrow checking is done here because, like as I said, non-lexical lifetimes. But kind of Mir is kind of like the core way that what makes Rust Rust, and it's kind of like the representation of the computer of what Rust is like. And as an example of what Mir looks like, if you dump out an example, again, this is a little old, and this like pseudo Rust, it's not actually Rust code, but it kind of looks like it. Again, we're printing a data structure that doesn't have a real text representation. So here you can see our add one function. It declares two variables, 0 and 2, or 1 is the first parameter. And in a BB0 stands for basic block. So to pay attention to control flow, we have this idea of blocks. And so it'll say, hey, storage live means that the second variable is live in this area, which is an analysis happens about control flow. It's too complicated for me to get into, and I'm too far in the weeds already here. You could read the docs in the compiler if you want to see all what's happening. But you can see our call to add adds a constant 1 and our number 2, and then declares the storage is dead and then returns. This is kind of what Mir looks like. Again, not anything you ever have to worry about as a Rust programmer, but if you want to see how the compiler sees your code, looking at Mir can be really useful. And then finally, Mir gets lowered to LLVM IR. LLVM is a compiler toolkit that you can use to kind of like build stuff. It's a VM in like the technical sense of VM, but not in the way that everyone uses the word VM. So it used to stand for low-level virtual machine, but the LLVM project changed its name so that it no longer references virtual machines because that got too confusing to many people. So basically, what we do is optimizations and code generation are done by LLVM for the most part. There are a couple optimizations that happen in Mir, and we hope to do more of them in the future. But Rust would not be anywhere where it is today without LLVM, so it's very important to us. And it kind of like is the lowest level of the compiler sort of operates. LLVM takes the compiler's output and produces the binary, so we kind of like hand it off to that library as the last couple steps. Andrew Livrette, sorry if I mispronounced your name, is asking, what is the timeline if there's one to get SIMD support on stable? So SIMD is actually already unstable for Rust, but only the x86 versions. So it's also the low-level unsafe primitives. So I think maybe you either, one, don't know that's true, which is totally fine, but that does exist today, or two, you're talking about higher level SIMD, which is like what you would want to write as a regular programmer instead of the intrinsics. I don't actually know that there's a group working on the higher level stuff right now. The low level stuff does work though, on x86 at least. And given ARM's recent interest in Rust, I'm assuming that ARM assembly stuff will be soon to follow. I think maybe some of it already works, but I'm not actually 100% sure. So yeah, still more work to do there. Don't know the exact timeline yet. Question by Jam1 Garner. What would go-tos be used for in Mir? Just more complicated breaks. Basically, like, structured programming is useful as the programmer. Like we write loops because we don't want to have to think in go-tos, but go-tos are conceptually simpler because they, are allowed to do whatever. And so it's actually easier for the compiler to understand than the higher level constructs. So I actually, I again want to emphasize, I don't work on the compiler myself, so I believe that go-tos exist, but I don't actually 100% remember, so I might be a little wrong there. So you should, if you care about this topic, you should look into the details a little more, but I believe that that's the case, but I'm not 100% sure. Finally, there's a question about working with Rust and Fuchsia. I will talk about that towards the end because it's not relevant to this part of the conversation. So I'll get back to you, SpaceX Jedi. Don't worry about it. Thank you for the question. Okay, if you're curious about what LLVMIR looks like, this is an example of the text version of LLVMIR. So you can see that the function's name is mangled, so it's add one, but with a bunch of other shenanigans on top of it. We add a number to that and return it. It's very straightforward. There's a whole bunch of attributes and other stuff. So this is kind of like what we hand off to LLVM. It does optimization passes. There shouldn't be a lot of optimizing to do in this code other than maybe inlining it into other code we've written somewhere else. So, all that kind of thing. Okay. The last thing I need to mention on the compiler architecture before we go back to how this works with additions, I hope you'll forgive my little compiler tutorial here, is that I said before we were a multi-pass compiler, and that's true, but we're also like working on making Rust query-based. So a lot of the compiler is already query-based. And what that means is instead of these kind of passes where you take the whole source code and you turn it into one AST, you take the whole AST and you turn it into here, vice versa, or continuing down that strategy. Rust instead uses this concept called a query to create an executable. So what happens instead is the Rust compiler will say something like, hey, what type is this function? What's the body of this function? And then the compiler will operate in that fashion instead. So instead of it being like, here's the source code of your program and turn it all into one way, the compiler will say like, give me where's this function? And then the internals, the compiler will say, oh, we don't have this function yet, but let's load up the source code of where we think it is, and then we'll look at the body and do all that work, and then sort of figure out that way. And so it'll sort of do all the steps, but in smaller chunks instead. And the reason this is useful is, first of all, memoization. So you're able to, reuse results of these queries across different invocations of things. And so that's helpful for compiler speed, but also more importantly, it fits incremental compilation. Couldn't say that. Incremental compilation, it fits it much better. And so, if we're able to just say like, oh, the body of this one function changed, that would map directly to one compiler query of saying, get me the body of this function. And so then you would only do that part of the work instead of saying like, okay, you change the body of this function. Now we have to redo the whole AST and the whole higher level IR and the whole mid-level IR. And so this is kind of the way that sort of production grade compilers are written today, rather than the way that they're taught in school. This was started by C# with their Roslyn compiler. So if you're more interested in kind of how this works, you should look into Roslyn or Rust C as we continue to make it happen this way. All the Mir stuff is written like this in my understanding. Some of the older code is not yet converted, but this would kind of be how this stuff sort of works. Also, if you've been following Rust Analyzer lately, it kind of has this sort of model of like highly incremental and like not traditional architecture that compilers have. So that's all how that goes. Okay, so additions aren't allowed to break everything, but like how does that mean? Like what's that mean? So for compilers, basically like additions aren't allowed to differ by the time you get to Mir. And so, what that means is a little fuzzy from the outside, but basically what it means is the core of Rust, Mir, stays the same no matter what. And that really matters for a number of different reasons. The first thing is that like, because it becomes a common language for all the additions, it's much easier for the compiler team to sort of manage changes that are brought on by additions. So all of the stuff that happens, differences in additions, happen at earlier stages than Mir. And so what that means is we can assume no matter what going forward that Mir is like relatively stable. Obviously they're changing the interface, but I mean like we don't have to switch on things by the time you get to that step. And so everything is sorted out earlier. And this happens to make interoperating between additions easier because your 2015 code and my 2018 code will both compile into the same Mir at the end. So that's how we can guarantee interoperability because they're both speaking the same language at the bottom of it. Because this is the primary mechanism by which things become interoperable. And it's also the way in which we can like control the amount of breaking changes. Because if you need something that would change things like very fundamentally, then we can't do it because we need to have this sort of interoperability layer. On a human side, not being able to break things in Mir means that things can change per addition, but not that much, because like the core understanding of Rust and what it is going to be the same no matter what the sort of like high level details are. And so that's really important. It also means because we are compiling down to the same thing, we have this interoperability, we don't split the ecosystem, and that really matters. Hey, Jared has another question. What would adding more query-based compiler features to Rust C make Rust Analyzer and other sort of analyses tools more robust? Yeah, basically that's exactly like the reason that C# underwent the Roslyn project is IDEs have very different needs for languages than the traditional compilers do. And so they kind of like reoriented it around what happens in an IDE. That's exactly why I phrased it as kind of like, oh, I changed the body of this function. Let's not recompile the entire world, because that's what happens when you're actually in your editor programming is you change little bits. Most of the program stays the same. So we kind of want to reuse that work rather than changing, throwing it all away every single time. And so, yeah, it's definitely one of the reasons why those tools are better is because they want this kind of architecture. So, yeah. Okay. And then another thing about like what is additions towards the end, you can kind of think of additions as sort of like a bigger release cycle. So Rust already has 3 different release cycles. There's stable, beta, and nightly, and there's different cadences to those releases. So nightly is every night, stable and beta happen every 6 weeks. Okay, so additions kind of like are like a bigger release cycle that happens, broader than versions, but we don't have a cadence for additions yet. This is kind of why this talk exists, and we're working on an RFC that I'll get to here at the end. But basically, like we didn't actually decide whether or not this would happen on a schedule or not when we decided to do it in 2018. So there's no policy in the initial RFC about when additions should be used, as I sort of just mentioned. It didn't talk about when, it just mostly was talking about how. And that way we could focus on shipping Rust 2018 and not worry about it until later because there's a lot of stuff going on. And we didn't want to set that policy immediately. We wanted some experience with additions. We wanted to get it 2018 going, and we didn't want to think about it basically. So now that it's been a couple years, it's time to start thinking about it. So 2018 was sort of the first edition, but we kind of retconned it to be the second one. So Rust 1.0 and Rust 2015 were the very first edition, sort of speaking. 2018 was the first one that kind of like changed things. And so what I want to talk about next is like a little look back about how that happened, because I think that really informs what we should do in the future. And this is also, again, kind of like why we didn't pick a policy back then, is we wanted to be able to see how it went and then think about the problem later rather than trying to invent it beforehand. So let's talk a little bit about Rust 2018 and kind of how it went. So I think overall Rust 2018 was a success. We achieved our goals, even though it was a ton of work, but we did ship the edition. It did happen. People did manage to understand this was different than Rust 2.0, and they didn't like run away thinking that we had totally destroyed our stability guarantees. There obviously were some people that were kind of not happy that we did any sort of changes, but you can't please everyone all the time. But the fact that it was a different kind of mechanism helped people understand what we were trying to accomplish. And I would say that there are not any real major issues with the addition system itself at this point. There's some tweaks and things, but like, the actual rollout of the implementation went smoothly for the most part. It was a lot of work. It was a really big project for all the teams. And we never really had undertaken such a big project before, other than maybe Rust 1.0, which is again, sort of kind of like an addition. And so we managed to do it, and that's positive, and that I think is worth like celebrating. However, Rust 2018 was also not a complete success, in my opinion. So there's kind of 2 different ways that I think that it really struggled. The first one was the schedule, and the second one was the team. So we didn't ship everything that we wanted to ship in the 2018 edition. Some things didn't actually get finished. Some things changed significantly, and scope had to be cut drastically in order to make it under the release line. And so while we did ship the mechanism and it was successful, it just barely happened. Like the release, as I'm going to talk about schedules in a second, happened in December of 2018. We actually did not have another Rust release. It happened literally at the last moment. And so that also is, a sign that things weren't necessarily as ideal as they could have been. Secondly, was the human cost of the edition. The team, tons of people put in tons of work for a really long time to make this happen. And it was extremely high stakes because this was a really big thing and it was the first time we'd ever done it. And so that contributed to a lot of burnout amongst contributors, I believe. I can only truly speak for myself. I was a total freaking mess by the time the 2018 edition actually happened. And I wasn't even the one implementing a lot of this stuff. I was just trying to like keep the book going and do some other work. So other people worked a lot longer and harder than I did. And I felt terrible, honestly. So I can only imagine with other people, how they felt about the schedule. So we did it, but like at what cost? And so, yeah, the 2018 edition shipped on December 6th, 2018 with Rust 1.31. And so What's kind of funny about the half shipping thing too is like some actual changes didn't ship until 132, but the edition itself shipped in 131. So yeah, we shipped a bunch of different things. This is a screenshot from the blog post. So non-lexical lifetimes happened in 2018. Module system changes got simpler in 2018. We did some more elision stuff. Constant functions became a thing. There was things like rust fix got added. A whole bunch of lints like Clippy was able to do its job on stable, and that was a big deal. Documentation got updated. We had the new domain working groups, a new website, tons of things happened in the standard library, lots of new cargo features. There was just like all sorts of stuff. Like 2018 was huge. It's a really big deal. And we shipped a lot of it, and that deserved celebrating. But as I said, it was behind schedule. So the initial RFC had sort of this schedule. There's this idea of a preview period, which is kind of like you can think about the edition being unstable. So the idea was that like, okay, Rust 123 is going to start shipping a preview of the edition, and then in 127 we're going to like nail everything down and actually ship it, and that'll be when it comes out. So to put some dates on that, 123 was January 4th in 2018, and the final 127 release was going to be June 21st, 2018, so halfway through the year. And if you're paying attention a moment earlier, that was very different than what actually happened. So what actually happened was the changes landed in the nightly compiler on the 6th of February. So that was almost 1 month later than the initial release was planned. And then finally, the actual release was in December, which is like 6 months, June to December, something like that, a long time later. And we kept thinking it was going to be in like October, and then that slipped, and then November, and then slipped, and then December, we finally got it out the door. So we almost missed the date itself, which is intense. I think that this happened because we tried to do too much. Partially that was because there was a lot of work to do. Like Rust 1.0 was a really small release, and there was a lot of things that really needed to be tweaked. We had this opportunity to do it, so we committed to it and we made it happen. I think another part of sort of some of the problems was some of these ideas we tried to move too far in front of the community. So like some of the things around, for example, the anonymous lifetime were added, and I'm not even sure that people like know about the anonymous lifetime or use it exactly because it kind of got lost in the shuffle a little bit. But we had some ideas about some patterns, and then it got scaled back, and then some things got sort of like cut or barely shipped. And we tried to like move too far ahead and think about like what things should happen rather than taking what happened and like getting the good parts of it. And there's always a balance to be had there. I think that added some stress. The module system was another example of this, where we like kind of invented what we wanted, and then there's a lot of changes and a lot of feedback, and it was really, really difficult to get that through. Finally, the other reason why I think we bit off a little more than we can chew, so we're really, really great that we have so many contributors to Rust, and we did at that time, but also contributors are not employees. And it's much harder to plan a big initiative that spans a whole year when you can't be guaranteed that there's like these people that have full-time amounts of work to work on it. Like just from a project management perspective, people are free to come and go as they please on the Rust project, but that also means that when you're trying to like get a huge thing shipped on a tight deadline, it's difficult to be able to rely on people having the ability to do stuff. And even if you are an employee, like I said, I got burned out. I didn't want to do this anymore to some degree, and so it can just be really difficult with these kind of big initiatives in an open source world. And I don't think that anyone has figured out how to really accomplish this yet. Another positive thing was we proved that the mechanism actually worked. So 2015 and 2018 interoperate just fine. The plan was good. It happened. You don't have to worry about this thing. We can have our cake and eat it too. Which is the thing we always try to do in the Rust world. We didn't split the ecosystem. There's not a holdout of people that use 2015 that like are sequestered from the rest of the community. And so that's like really important. There are still people that program in the 2015 edition today, and they can do everything they need to do, and it works just fine. So that's, I think, a really important thing. We've kept some coherence. And I think that like it works so well because it's pretty much silent. Like I don't think most users think about editions a whole ton, which is part of why I wanted to start this talk by putting out all the details, because like it just kind of works. You don't really think about it, I think, for most people. And that's a testament to how good the thing that we shipped was. But as a downside, we underestimated the cost of the edition to both the human element, but also to like our users who needed to make these changes happen. So even though we put a lot of time and effort into making upgrading easy or simple, it wasn't actually so in the end. And that's just because there's a lot of moving pieces. So we had Rust fix, which was able to automatically upgrade your code, but like it wasn't perfect. And there were some things that couldn't necessarily update, some of the fancier features, and people still have to like validate and test and do these kind of things. And so it just takes a lot of time. The compiler did not shift to Rust 2018 for a little while, neither did other big projects. And I think that's also okay. Like expecting everyone to upgrade immediately is part of like an unrealistic expectation. And I don't think we totally had that, but there's definitely some people that thought that should happen overall, like in the community or on the teams, because they worked on smaller projects. But some production users reported that it took them a while to upgrade to 2018, and it was a significant, costly kind of upgrade. Even if it's easy to do, it still takes time, and time is money to companies. And companies are the ones that have the biggest Rust projects because they're paying people to work on things full time. And we sort of put a big burden on a lot of our biggest users, and that's tough. So I think it's a challenge. I think another thing that happened with the 2018 edition is it became feature driven instead of time boxed. So, normal Rust releases are time boxed. That is, there's a schedule and the release happens, train leaves the station, regardless of whether you make it or not. And so that's kind of what happened. And Rust 2018 sort of became designed around features. So we sort of said like, hey, what features do we want to happen? And then we figured out how to make them happen on the schedule. But then when they took longer to implement, then maybe we thought, that became kind of an issue. And so that was, I think, a lot of the struggle was like, we need to get these features out. And there's this time deadline, and we have to have it happen before the time. That doesn't happen with normal Rust releases because there's always a new train coming in 6 weeks. Like part of the reason why we picked the train model in the first place is because we knew that having a yearly or longer release schedule was a problem. So then we decided with the edition system that we were going to do that. And so I think that was like a big issue. Kind of felt like the lead up to Rust 1.0, where there was this big giant release that happened and everybody worked super hard. This was a huge amount of hard work and Herculean efforts by folks, and therefore some burnout happened. And so I think that was a big problem with 2018, was getting too caught up in like, it means this set of features and we're going to ship them on this day. And so a great example of how this did not happen and was very successful is async await. So, we realized that async await was not going to make it in 2018. And so we said, hey, we're going to reserve the keyword so that we have it in the edition, but we're not actually going to release the feature. And so what that meant is that, so 2018 December was when the edition shipped, but we actually shipped the async await in 2019 instead, almost a year later. And I think that worked out really well and is a great model for how this should sort of work in the future, is that we don't necessarily we don't force everything to happen, and we don't force the schedule of the edition to happen on a feature basis. We kind of just say, hey, the feature is going to be on this cadence, and we're going to ship the feature when it happens. So that's important. This is kind of blending into the last part of my talk here. What should we be doing? So this is kind of like my opinion on where we should go from here. Basically, we should have a Rust 2021 edition. I know that every talk with a title in it is supposed to be no, but the answer is yes. Gotcha, Betteridge's law of headlines. But I think that we should have a 2021 edition, and we should commit to a train model for editions, and we should have one every 3 years, no matter what. I think that this should be smaller than Rust 2018 was, for a number of different reasons. First of all, I don't think we have as much need as we did in 2018. But secondly, I think that it will just go smoother if we don't do as much. And I also think that a lot of people are sort of craving stability in the Rust world. And so I think that that's like a very positive thing. And so a smaller edition would be much smaller than 2018, but I still think we should do it anyway. There's a question from Emmanuel Lima in the chat. Does Mozilla hire engineers to work on Rust C, and that should help diminish burnout? No. Mozilla does pay some people, but it's a very small amount of the overall team, and there's no indication that Mozilla is like going to hire 10 more people, which is like what we would need. So yes, while they could in theory do that, I don't think the Mozilla is going to, and I don't always think that just hiring people is always the right solution either, because it depends. Like we could hire the community and that'd be great because they already know what's going on, but that doesn't necessarily mean that that's the right call, because like not everybody wants to do Rust as their job, and like it's complicated basically. But it's true that work helps diminish burnout, but on some level, work can also force you into burnout, because when it's your job, you have to do it even if you don't want to. So like deadlines are somehow weirdly more stressful with jobs than they are with open source projects, I think. So, like I said, I was a Mozilla employee at the time of the 2018 edition, and I got burned out anyway. So I don't think it's a pure solution. I do think that can help in some cases, yeah. Okay, so release trains, like the core of my argument about the 2021 edition, release trains are good, and editions are kind of release, so we should have a train, and that should just be the end of it. Like we should no longer pick date-based releases. We should just always do trains because they're just far better way to ship software. If 6 weeks go by without a new release and a new feature in the regular code base, we still put out a new Rust C anyway. Some releases are small, some editions are big. That's just the way that it goes. And so I think that if there's 3 years go by and we don't need any big breaking changes, it's totally fine, but we should still release a new edition. Sprudalel asked a question in the chat that I'm going to be getting to very shortly, so stay tuned. But yeah, like basically, I think the train model has been wonderful, and I think that we should do it with editions too. There's a number of reasons. I'm not going to get into all of them, but basically, like the shortest version is it's a model that works and is a model that we've demonstrated is feasible. So I think we should just do the same thing, but on a longer schedule. Some people argue that the social part of editions shouldn't matter and that we should only make editions happen when we have the feature need, but I think that that's wrong. Some of it is just the classic arguments back and forth that happen the first time the edition happens, like looking over the past 3 years matters, getting people outside of Rust to pay attention to stuff matters, and all that stuff still happens. I think that smaller editions are actually a nicer marketing message, so shipping them is somehow more important in some ways than a big breaking change release, because it's like, hey, it's been 3 years with Rust, and we don't feel the need that there's any big breaking changes because we think the language is good enough. That is a very strong and powerful marketing message to people to be able to want to check things out. People are still like leaving comments on the internet all the time about like, I don't know that Rust is actually stable because of the 6 week cadence. Like people don't necessarily know how much time and effort we put into making sure those things are stable. And so, every 6 weeks seems fast. So if people get on the idea of like, oh, I only deal with Rust every 3 years, it feels better to a large number of people. So I think that really matters. Yeah, there's another question on Twitch I will get to in 1 second. Okay, Sprudalel, here is your question on a slide. So what features should be in Rust 2021? I actually don't care personally. There are some features I want, obviously, but I think that we should do it regardless. And I don't think that we need to have a specific feature to justify doing an edition. In fact, I kind of think the argument is stronger purely on the like release engineering and marketing angles and not on the feature-based things. Part of this is also because like consistency and scheduling overall is key. If we miss something, then it misses a train, it can get on the next train and that's fine. But like if we release editions based on features, then every time we have a new set of features, we have to relitigate this entire conversation. And we already did it first with 2018 edition, and we're doing it now to set up this policy. And I would like to not sort of like have the Rust team be arguing every 3 years whether or not we should be releasing an edition or not, or arguing like even more often than that. Like, if we do it on a feature basis, then it happens at random kind of times. And if we just say like, hey, this is the mechanism, it happens on this schedule, period, then we can free our time actually working on making Rust a better language rather than worrying about this policy. And so I think that that's actually the like, sort of most important kind of thing. I will answer that question, Predco, afterwards. So why a 3-year cadence? It's just like a nice length of time. C++ has a 3-year cadence as of late, and yearly is too often because like there's not enough stuff to sort of accumulate to make it a big enough deal every year. 5 years would be far too long in my mind. So I think 3 is kind of a nice compromise, and it fits similar to C++, and so I think that happens. Specifically, I bring C++ up because C++ OX, I think, is a cautionary tale that we didn't really learn enough for the 2018 edition, and it feels very similar to the 2018 edition for me. So the first draft of this standard of C++ was in 2008. C++ 03 was the previous year of the standard. And so Bjarne and some other people were hoping that this would be C++ 08 or 09. So they named it C++ OX. The problem was that they made it on a feature basis, and it took them so many years to get through all the details, and ended up shipping in 2011. And so people used to joke that it was becoming C++ OA because like they had missed, like with the 08 or 09 scheme, it slipped to 10. So it should be C++ 10, but they'd already said OX. So like, this demonstrates some of this kind of like conflict here. And so that's when they decided to move to the train model for the C++ releases, was like, we're releasing every 3 years because like this was just not great. And so I think we had a similar kind of learning from 2018. So I think that matters. I'm going to answer some more of these questions afterwards because I'm almost done with my slides, and then we can get into sort of the details. So specifically, and this is kind of like the second part of your questions, Brutalel, earlier. So there's this comment on the internals forum recently, like, hey, the roadmap for the year, what things are we actually going to do in 2021? So even though I don't think it matters, I should talk a little bit about maybe what I see happening. So this is the text from the original RFC. I'm not going to read all of it, but if you want to go read it, you can. But what we talked about this year was we're going to prepare for an edition. So the goal should be any changes we make for 2021 are completed by October of 2020. So we should know what's going on. So it's the end of July right now, so that gives us a couple months, but we should have the plan sort of like in. And also we said like we had not decided whether we were doing 2021 or not. So we should also decide that we're going to do it. And so like I said, this is my opinion, but technically the project is not decided. So that's also the work to do immediately and part of deciding to do it is sort of deciding what should be in it too. So there were some things about what might happen in the RFC. We talked about maybe error handling might be a good thing to address because that's a big topic lately. Improvements on the trait system or improvements to unsafe code, but the goal is kind of like to figure out what that is. And so we should have some specifics on exact features kind of soon-ish. The language team has had a few discussions on this, and as far as I know, the goal is still to have a specific plan about editions in October. But as I said, we still have to kind of also decide if we even want to do an edition. My audio cut out. Okay, this is not formally done yet. So, we also need to plan that. And so I think that even the stuff that the language team is talking about is nothing like 2018. Like the scale is very, very small overall. They're like kind of smaller details about things. As an example of one thing that's been talked about, I don't know if this will happen or not, or what the chances are even, but there's been some discussion that like unsafe functions should be able to call unsafe code in their bodies without an unsafe block. Or you should need an unsafe block. I forget which order it is, but there's like things like that that are like really tiny edge kind of things, and nothing like the module system is being redone. So I think anything that happens in 2021 will be important and matter, but like will be relatively small changes and not like we saw what happened in 2018. There is going to be an RFC on this question of policy. Nico and I were supposed to be working on this, but honestly, I got busy with my new job and Nico did most of the work. So we should have something published relatively soon to answer this question. And then we can have this discussion as a community overall because, it's not, the teams do get to decide what they want to decide, but we want feedback from everyone to talk about all the details. So, that stuff kind of matters. So you can expect to see an RFC in the near-ish future. Talking about the policy of whether we're having an edition or not. And then also the language team, if we decide we're having one, the language team would be able like what is actually an edition. So that's all going to come over the next 12 months. So thank you for listening to me talk about that for an hour. That's the end of my presentation. And now there's some questions that were in the chat I definitely want to cover. So I'm going to go from the start to the end of the ones I did not answer already. Okay, there was a question from someone whose name has a lot of numbers in it. I don't know how to pronounce it. I'm sorry. Does it seem reasonable to you to make an edition a snapshot of already shipped features? So keeping features opt-in until the next edition while making them shipped and stable as opt-in. I think that's nice in some ways. I think that doesn't always work in some other ways. So like what I would sort of like to see is that we have these like features that need an edition break. You're sort of able to opt into the edition on unstable. So it's kind of like that preview idea that happened before. So basically like, the feature exists and we're able to try it out on nightly, but it's only about tweaking the edition rather than tweaking all the details. And I think wherever possible, we shouldn't use the edition mechanism. Like making things a breaking change should happen only if they have to. So talked about the async keyword being a breaking change, but I think that like, the union keyword, for example, was a contextual keyword, and we didn't need to do that in addition, so we didn't. We could have, and maybe it would have been simpler, but I think that where we can ship it on all editions, we should, and we should only do it like when we actually, need to. So that's the thing that matters. Okay, so Predko Sylvester asked a question about why we don't have function overloading. So is this a historical situation or some design background? Kind of not exactly related to my talk, other than in theory, this is a big feature that would make sense for editions, I guess. So, one simple example of why Rust doesn't have function overloading is no one has ever written an RFC to suggest adding it. So some people have written pre-RFCs and some people have done some of the work, but like on its core, most features in Rust don't exist because people didn't do the design work. Now, this is a little controversial with this specific feature because, like I said, some people have gotten up there, and I think there's actually an open RFC right now. So maybe what I want to say is there's no accepted RFC, but I think that specifically function overloading is interesting because Rust does have function overloading today in terms of traits, sort of. So it's not the same as like when you think about I write a function with different signatures and like you figure out how that works, but like you can do that through traits, sort of, kinda, and that is, I think, enough for most people that the idea of regular overloading is, a bit too much. I think also this is hard because function overloading, optional arguments, and named arguments kind of all are three features that are technically separate, but are something as a language designer you kind of want to consider holistically, and that's a really big design space. And so there's also some people that are interested in those other two features as well, but you kind of really, in my opinion, and I'm not on the Lang team, so again, this is my personal opinion on this. These are like a large amount of big features that I don't actually think buys you that much personally for me. So I don't really want to see these features added to Rust. But that doesn't mean they won't happen. Like I said, I'm not on the relevant team, so my opinion is just contributing as a community member, just like anyone else's. But I think it's a huge design space, and I think that most of the benefit is already there. And so I personally don't think that it pulls its weight. One thing I will say on the named arguments front, though, is with Rust Analyzer putting the names of arguments displayed in the text, I have found them more useful to see that than I would have thought. So it's actually made me feel a little better about named arguments than I would have otherwise. But I think that again, Rust Analyzer doing that gives you all the benefit without changing the language. So putting in the language seems like a lot of work and doesn't really get you a ton of benefit for me personally. But yeah, I think the core challenge is that it's really hard to put all three of those features together and design them all at once. That's a huge space and it's very difficult. So I don't blame anyone that cares about this feature that has put in some of the work that's kind of like not made it happen, because it's a really big topic and a really big area. And it's really hard. Okay, so Floor B is talking about being in the only make additions happen when there's a need camp. A big part of that is that the social and technical aspect are conflated. Would it make sense to separate them more? The addition is a social event, and the addition is in cargo.toml. I do think that this is like a coherent point of view, but I just personally disagree. I think that part of that is because you need the social side to advertise the technical side. Like, they're inherently intertwined. And I know as programmers, we really like to separate out things, and we want everything to be kind of in its own little box. But I think that specifically, like with big major changes to the language and ones that are breaking that you're gonna have to learn about and stuff, there has to be some sort of social component of letting people know that those things exist. And so, like, yeah, you could argue that like we should celebrate what we've done on a different cadence than the release of the actual breaking changes, but like that just means we have kind of like two major points where we need a bunch of communication. And I think that it all just works better by leaning into the fact that they're actually not separate. I do know that there are some people that feel very strongly that I'm wrong on this, and that's also totally fine. Just for me personally, I think that it's not really possible to untwine them, and it's actually a good thing that they are together, because like you need to be able to communicate those things, you need to make it work out. So I don't know. Okay. Jan1 Garner says, should the 6-week cycle changes also be listed in the 2021 announcement to be closer to the other language release? So yeah, so what we did like specifically was that. So that blog post that I showed the title of, it included the changes that were in the things all together. And you could argue that maybe they should be like two separate ones. Kind of what we did last time was we blogged before the edition actually happened to kind of talk about what was going to happen. And then the release post was kind of like more of, describing the changes in detail. So it's kind of a way to split that up a little bit. To some degree. I think that when you start to separate it out too much, you get into the exact problem that we were talking about with the last question, which is like, I think they need to be around each other because you want to communicate them at the same time. So I do think that including them all in one thing, or small, maybe like in like a month kind of area sort of thing. But yeah, I hope that answers your question. Jack asks, Jack asks, to be clear, would it be another 3 years till it's available, or just available in the next Rust C? So like, basically, I think that we should be flexible a little bit about the exact time when we stabilize the edition. Like, I don't think we should commit to a specific release because I think that's what introduces like a lot of the problems. It should just be sometime in that year. And so I think this is part of also why it's like the Lang team has to have its stuff planned by October of this year, because we want to be able to release it sometime next year. And so if we have stuff done in 2020, then there's a whole year's worth of time to have the schedule happen, rather than trying to, say, okay, we're going to start thinking about this at the beginning of the year. We're going to ship it by the end of the year. Just like if we're ready in advance, that like helps alleviate that schedule pain. Excuse me. Okay, also, oops. Ooh, talking too long. Also, wow, okay, guess I just totally lost my voice, sorry. All right, so also, I think that having the time before things are released matters, because putting something in edition that has a breaking change, as I said, it impacts people a lot. So we should do so very carefully. And so I think that one of the sort of like problems of 2018 too was like we had these grand plans, we threw them all in together at the last minute. In some sense, like we should be more deliberate about what goes in the edition, and therefore we should have to plan it earlier in advance, because that means that we only are willing to do it for things that really, really matter. And so I also think that things should be planned ahead of time because of that. So yeah, so it should land in Rusty at some point during the year of the 3 years, but I don't think the specifics matter that much. And so another comment on that question was, what does it mean if something, well, audio, there we go. What does it mean if something misses the train? Like say we had a GC, which is not a thing that can happen, as you say, but it missed the train. Would it be another 3 years? Yeah, so it would have to be another 3 years, unless what missing the train would mean that the stuff that needs to be backwards and compatible would miss the release. So imagine if we did not make async a keyword in 2018, it would have to be a keyword in 2021, and that would mean that like async await couldn't have shipped yet because the time wouldn't have happened. So I think the feature implementation missing the train is totally fine. Like that's what happened with async, right? Like the breaking change made it in, but the implementation didn't happen until later. Great, I think that's totally fine. And in fact, I think is the model that should kind of happen, is that like the stuff that is breaking that's not ready yet, we don't worry about making sure that it's actually happened exactly by the time the release happens. And some of this I think is because too, it takes time for the ecosystem to catch up. So for example, with async, like async, even if async await had landed on the day of Rust 2018, the ecosystem would not be ready yet. And so for most people, like it's already been almost a year since async await happened. Time flies. And the ecosystem is really still only now finally getting into a production ready state. Like async await wasn't really a 2018 feature. It was really a 2021 feature. And so I think that like really a lot of the edition stuff should be looking back over the last 3 years rather than looking forward to the new stuff. And so like in some sense, the stuff that we reserve in this edition, gets used by folks and like is only really part of Rust world until the future. And I think there's some weird interplay there. And that's also why it's kind of hard to do these kind of bigger macro level changes and thinking about things. So I hope that answers that question. Okay. Andrew Lefevre says, has there been any advances with having an unified async runtime instead of having conflicting runtimes like Tokyo and Actix? So yes and no. Like I think that there's two things that are tied up here. One is that I don't think it's possible to have a unified runtime for everything because Rust is used in too many places. So for example, like I'm a big fan of both of those projects, but I also do embedded Rust work now, and there's some stuff that maybe would be good as asynchronous. I'm not going to be running Tokyo on like my embedded device. So I would need an embedded executor that makes very different trade-offs than Tokyo. Tokyo is built for network services specifically, so it's made several trade-offs that make lots of sense for those things, but it wouldn't make sense for my microcontroller. And the same token, like if I was building a web service, I wouldn't want to use my microcontroller async await impl because it made the wrong trade-offs for me. So I think that it's not possible for what Rust is trying to accomplish to have a unified runtime. That said, it should be possible to make libraries runtime agnostic, so it doesn't matter what runtime I'm using. And that's like kind of one of this open things that's still being worked on. And Like, I don't think this is the kind of thing that happens from a big top-down perspective. I think that it just takes time in the ecosystem for folks to hash out what they need and what's going on. And then we compare experiences and we consolidate where possible. So there hasn't been any big news on that front lately, but like all the people involved are still working on it. And I think everyone cares about making things agnostic, at least conceptually, because nobody wants things to be locked down into one specific area. So it's just really tricky. But a lot of libraries are agnostic today, but not as many as there could be, and there's still more work to do there for sure. Um, all right, another question from League 11. Is there any intent to sync the edition cycle with major distros and/or Windows major release cycles? Because that might be useful for CentOS, Debian, etc. Um, Not really, because the problem is that all of those things have different cycles, and you can't really release them on the same. Like you're going to leave some people out no matter what. So really, we kind of just got to pick our own schedule and just kind of be done with it. And that's sort of unfortunate. I definitely agree with what you're getting at. That would be really nice, but just like it's not really possible, basically. And yeah, I am doing great now. Thank you. It just took a while to get out of burnout. Okay, so best question. It's basically like there's only 15 minutes left, and I almost lost my voice, as I said. So there's still more questions I've not answered. I apologize if not get onto them, but we pretty much don't really have a ton of time. So I'm going to now pick somebody who asked a great question to sort of raffle off the book. So there's we're going to leave it sort of that. So let me think here. What I think let's go with Flora B's question, because I think that it was big and it was on topic with the topic, and it was like against what I'm saying, which is always fun, asked in a nice way, and a thing that matters. So Flora B on Twitch, you're getting picked as my best question, although I do appreciate all of them, and I believe that means you get a copy of Rust in Action, if I remember the details right. So that's cool. The last couple questions I didn't really get into. Sorry about that, but if you want to email me, I'm happy to talk over email or whatever else. So thank you so much for listening, everybody. My voice is dying, so I gotta go.
Już.
Hello, my name is Michalina Kotwica, and today I want to talk about low-level optimization of algebraic and similar structures, which is actually the reason for me to present that is basically that that was my research topic for my master thesis, as you could have seen in the description of this speech. I'm not a professional Rust programmer. I used to code in Rust during my time at Intel Poland, but I use Rust as a hobby and for side projects for a few years now. So I hope that you will find my presentation interesting enough. So first, I want to tell you what is the plan for the presentation, because I hate presentations without decent plan. So first, I want to show you some math theory that I will use during the other points of the presentation. Then I will present you what is the unit time and type and never type. So very special types that are more or less unique to Rust. And then some optimizations of structures, then some optimizations of enums, then some code statistics that I made, that I gathered from open source repositories for checking some popular opinions about the stuff I'll be talking about, and then something that is that I consider quite trendy nowadays in Rust community, futures or asynchronous execution, if you prefer to put it that way. First, the topic of the talk is algebraic structures, but if you search for that phrase in the book, then you will not find such a thing. What you will find is chapters number 5 and 6. Number 5 is for structures and number 6 is for enums. So the problem here, or the gotcha here, is that the way it's named is comes from the C family, while the algebraic structures is more of functional programming way to put it. So that's one of the differences and one of the reasons why it's not that obvious what's the meaning of the things I'll be talking about. So first, I want to show you some maths of type theory. So algebraic structures have basically two key operators. One is multiplication and one is addition. So first, if you have a point from the previous slide defined by x, y, and color, then it's multiplication, because if you take the number of values of that x field can take and y can take and color field can take, then if you multiply them, you get the total number of values that point can take. And for event from the previous slide, that takes one of three types of event. It's summation, because the quit variant, the key press variant, and click variant are separate. So it's not like for each variant of quit you have one variant of key press, like in point. But what is important here, and that's why the lower part of this slide is slightly bigger than the upper one, is that while for multiplication, the set theory and type theory and how it's coded in Rust is basically all the same. And for events, it's a little bit different, because for sets, it's not just summation, it's a special type addition that preserves the source of the value. So if you have two variants that have no value, then they are differentiable. That takes single value, or for example, if you have two variants that each have an integer. So these are the basics, and the reason why I'm showing you this is that if you have multiplication, then you must have a single unit. So it's the analog of number 1, while in addition, you must have the analog of number 0. So neutral elements of this operation, you might say. So for multiplication, it's obviously 1, because everything multiplied by 1 is the same number. And it's pretty much the same in Rust. So you can have a structure which has 0 fields. So it only has one value, it's the value. And the most popular way of expressing that is an empty tuple, because there is only one empty tuple. You cannot parameterize it by anything. And the most used and the empty tuple is the most used as the return type of the main method. However, it's also pretty useful for generics, because you can parameterize generics using empty tuple to show that the information of some variant of an enum is important, but it carries no additional information. And one of the examples is result with empty tuple as the error type, as you can see here. The reason why I'm showing you what it translates to if monomorphized, so if getting rid of the generic arguments, is because for the empty tuple, it's mostly obvious. It's not so much when we get to the analog of 0. But what is important here is that Rust has the way of dealing with empty tuple quite different from other languages from the C family, because the size of the empty tuple is actually 0. So be aware that if you create a generic type which doesn't handle well types that carry 0 bytes of information, you might get into trouble. So remember that you actually can create a vector of empty tuples. So 100 of empty tuples is still the same size as empty tuple, which is quite useful often. But what I found even more useful is the analog of 0, which is never type, or exclamation mark if you want to be graphic, or infallible type if you want to stay on stable Rust. It's, I think, most known for results which do not carry any error variant, but it's also used for expressing that the function never returns since the name. For results, it's actually a little bit tricky, because it actually deletes the whole variant that it occupies. So the result that has never as its error type actually never errors. So you do not even have the error variant. So the whole enum is just a single value enum. It only has a single variant, so you can even pattern match it to the OK variant, as you can see below from str trait. What is quite interesting here is that the never type that is lacking in other languages like C++ or Java, makes it possible to compose, not only compose the algebraic data structures, but also discard parts of them without suffering runtime costs. Because as you can see here, we do have our result of computation packed in the result structure, and still it only occupies the bytes needed to actually store the t-type without sacrificing any performance or memory for the error variant, because it's never there. For the multiplication, aside from the unit type, there is that one optimization, or one major optimization, I'd say, that is also lacking in C and C++. And the reason for that is that C and C++ are very heavily relying on ABIs, meaning it is important for C and C++ how exactly the bytes of some structure are laid in memory. While in Rust, data structures are a little more abstract. So in this particular method of optimization, we move the fields around so that they occupy less space. So as you can see, in C, the order of the fields in the memory layout is exactly the same as the one in the declaration, which you can check by your not use your rep C. Then you can see that Rust structures don't really care about the order you declare your fields in. What is quite important, though, it does not work if you use nested structures. So if you use anything like a tuple of substructure, a structure as a field, then it's disabled. And the reason for that is pretty much the same as the reason for lack of multiple optimization in C++, because of the language rules. So if we want to take a reference to the said tuple, it needs to have the same memory layout like any other regular tuple in the memory. So it has to occupy the same bytes. And therefore, we can't just separate its fields. And because of that, Rust can get the same memory layout as C if using nested fields or nested structures. But otherwise, it will try to reorder the fields in the most compressed way possible, and there is even a special fragment to ensure this. For coproducts or enums, we have even more optimizations. I think most useful ones on a daily basis is the optimization of Boolean, non-null pointers and non-zero numbers, which is quite similar to how things are all pretty often handled in C. So if you have a pointer and you do know that it's not null, you pretty often will treat null as an invalid value, or to signal the user or developer that this pointer hasn't been set at all. And in Rust, of course, the analog of that is an option type. And just like you would do in C, the non-variant of the option is occupied by the null pointer, because the null pointer isn't a valid value for, let's say, a box or a reference, which is not the case with just any usual pointer. And just like with pointers that do not have the null value, we do have numbers like usize, for example, that treat 0 as invalid value, which makes it work pretty much like with pointers, considering that null is pretty much always non-binary 0. With Boolean, it's a little bit different because false and true usually map for 0 and 1, but because of that, the 2 or 3 are still there to be used. So the non-variant is equal to binary 2. But either way, it's the size is reduced by that optimization. You may wonder what the dots here mean. On this slide, the dots are there because in the C representation, each part of that layout takes full 32 bytes, I think, 32 bits, I think, yeah. And in Rust, it's a bit more compressed. Another optimization which may prove useful to you in day-to-day life is coproduct flattening, which means if you have an option, then the memory layout is pretty obvious, because if it's not a null pointer or a 0 value of the non-zero type or a Boolean, but it's just, let's say, a byte value, then obviously you do need to store the information on whenever the value is valid or not. So you do have the part for the data and part for the so-called discriminator, which discriminates which variant of the enum you're at. And in theory, if you have an enum of an enum, so for example, a result of an option or an option of an option, then you should get another discriminator for the outer layer. But in practice, for simple cases, Rust will flatten the discriminator. So, for instance, if you have an option of an option, then it will be flattened into a single discriminator that treats sum of sum and sum of none and none as 3 possible variants of the new enum, which saves quite a lot of space if you have multiple layers of that, and especially many layers if you have only if you consider how many enums of the kind of option and result of unit and async, etc., you can stack together. But as I mentioned, it's only for simple enums, and what I mean by simple is enums that have at most one field that that holds any information more than just what variant it is. So in practice, it looks like an option. So for example, it could be a result with the error type of unit or anything similar to that. So as you can see here, if we use a result with error type of, let's say, a byte or an integer, then the optimization is disabled, sadly. Well, it could be applied, but it wouldn't be so trivial, and therefore it should be discussed how it should be done. To show you why that optimization is a real feature and not just some minor stuff, I want to show you some statistics that I gathered by scanning code of some open source repositories. So I took some some standard Rust repositories, so Rust C compiler, Serde, Tokyo, regex, my own master thesis, Google APIs, and Logger library, gathering more than 1,000 of enum declarations. And here is what I found. Most of enums are 2, 3, 4, maybe 5 variants they have. Some of them have 1 or 0, and no, there aren't that many of them that have more than 5 variants. It's pretty rare. And if they do, they mostly do not carry any data other than the information about which variant it is. And it made me wonder, okay, so I have 2, 3, 4 variants, but it doesn't mean that I only have 1 field on them or 0 fields on them. So what I checked is the maximal number of fields in variants, and that result was even more interesting for me, because over 40% of them had 0 fields at all, so they were enums in the classical C sense, and about 1/3 of them had at most 1 field, so a variant that is basically a wrapper for another type, which makes sense if you think about it. And then it's less than 15% of enums that have 2 fields or more in any variant. So that alone shows that optimization may be nice, considering that it works for enums that have 0 or 1 fields at most, and if they have 1 field, then only in 1 variant. So I checked, okay, but if the maximal number of fields is 1, then what is the minimal number of fields, or what is the number of fields that are non-zero? And it turned out that in most cases, if we have an enum with 1 field at most, then in most cases both variants do carry a value, so that optimization doesn't apply, but it's over 15% when it does. So as I said, the numbers that look like an option are pretty widespread, actually, because 1 in 6 enum declarations are of that kind, and they can flatten. So if you ever saw an enum that has multiple layers of other enums inside of it, in its monomorphization, there is a pretty big change. It will be flattened, and therefore you will save both memory and performance. And the third thing that I wanted to show you, that is also let's say it's also connected to algebraic structures, are futures. And you know, it's not that that obvious to see, because enums and structures are the dictionary definitions of product and coproduct from type algebra, while futures are that abstract thing that is defined by what it does. It's a trait, right? But considering how it's implemented in Rust, both futures and iterators are actually implemented as enums. So if you ever implemented a future on your own, then you probably do know it. So if you take some imperative code that uses the new async await syntax, it actually gets compiled to something that I wouldn't call an algebraic structure per se. That's why in the title of my presentation I called it similar to algebraic structure. And here is why. While I can show you the enum representation of what the above code compiles to, which is the block future here, it's not entirely true what I show you here, because you see, if you take just any normal enum, then if I go from the enter stage, which is when I enter the future, and go to the signal next stage, when I wait for the next signals to arrive, then I should move the signals from the block future and then create a new block future of another variant and move the signals back there. And here is the problem. It's a nonsense, because you move the memory around for nothing, because we statically know that it will be moved back, or at least it can be moved back. And in this case, it's especially silly, considering that from the awaiting for the next signal, we go to sending the data of that signal to some target, and then we go to the signals again. So we would move the memory around for no reason inside of a loop, which is even worse. And because it's so much against the Rust zero cost motto, it's not actually implemented that way. What could be done is, of course, implementing the block structure as a structure instead of an enum. And in this particular case, it would be a good idea, probably, because we use signals all the time, and the only things that would reuse the memory are the ID and data and error is probably not that big, huh? But in other cases, well, it bloats up to potentially enormous sizes. So the problem here is it's not really obvious what is optimization, because optimization should have a criterion. And on one hand, we have a structure representation, which bloats the size but boosts the speed. And on another, we have enum representation, which boosts the speed, which boosts the size but bloats the speed. So the solution here is to use something that is similar to both in a way. So we check which fields are available at which stage of the future execution, make it a table or any graphic representation you want, and check which fields are used at the same time. And if they are never used at the same time, then they can reoccupy the same space. Just like here in this example, if we have some bounds or indexes in a vector and an iterator based on them, and the iterator isn't available on the same stage of the future execution as the indexes, probably. So it can reoccupy the space. And conveniently, because the iterator over a vector is just twice the size of an index, then it reoccupies the space perfectly. So now we have the size of the future cut by 1/3, which is quite nice, but it doesn't really show the true power of this optimization, considering that many futures used to be kilobytes in size before turning on this optimization. And as you can see, this optimization of futures, which I called coproducts on steroids, is somewhat a combination of the field reordering, because we are definitely reordering the fields here, and the coproduct optimization, because we do a similar trick to what we did with not null pointers. Any questions or remarks for that part of the presentation? As I said, the rest is pretty unique in the low-level optimization topic, because the optimization are enabled by the language, just like they are prevented by languages like C and C++, and not really needed in languages like Haskell. And it's the best example of that I know is optimization of futures that I showed you. Okay, so let's see your questions. Lucas Prokop from YouTube asks, does flattening of the discrimination of result occur as well? Thank you for your question, Lucas. Yes, it does happen as long as one of the variants of the result is unit type or a never type. Well, if it's a never type, that it's not an optimization, actually, of course. If it's a unit type, then the result is practically working like an option. So it works for any enums that look like an option, you could say. So they have at most 2 variants, and at most one of them carries some information. Well, I heard that there are plans to enable more than 2 variants, but then you would need to have more fields that have that particular this particular characteristics. Like if you have a single variant of 2 pointers, then of course you could encode other variants by null on either of these pointers, but then the problem with that is that you would need to do multiple checks, which isn't really good for performance. So that's why it's tricky and not really that trivial. Yaimokond on Twitch asks, where are the user statistics from? I missed the early piece of the talk, so apologies if that was covered already. Yes, it's my original research. I just scanned them with a Rust tool for parsing the code. So I parsed the code and I just used kind of a grep-like thing, you could say. Jamwan Gainer from YouTube asks, I always heard the internal representation of futures being represented as a state machine. Yes, the enum is an implementation of a state machine. As you could see on the slide of mine with that enum representation, I showed you the state changes or the possible state changes by arrows. It's a little more explicit in the next slide when you have a table with availability of the fields. So the state machine is the abstract concept, and you are right, it is a state machine, and enums and structures are the implementations of the state machine. Chris, please, from Twitch asks, so option of non-zero U8 can be optimized into single byte by reusing the 0-bit pattern. Yes, exactly. How close are we to generalizing that the other bit patterns? For example, if I have an U8 like type that's never... Oh, yes. There have been discussions about this particular example that you used, the FF pattern. Well, there are two reasons why it's 0. First is that comparing to 0 is the fastest of the comparisons between variables and literals, just because of how it looks in the machine code. But in fact, there is no reason not to generalize it. The main problem is that this optimization is built in the language, so it wouldn't be obvious if the change is optimal in the performance sense. It would be in the memory layout sense, of course. In fact, if it's FF case, or -1 is also a popular idea, then nothing stops us from that, I think. And I've actually seen some implementations of that, and I've done an implementation of that myself. As for checking if something is less than something or greater than something, not so easy on the language level. So the problem here isn't the technical aspect, but it's the safety aspect in this case. The safety aspect and the proof that it's indeed more performant. So you could say that it's 0 because we don't want to wonder if it's the best choice both performance-wise and size-wise. Scrabsha from Twitch asks, would that be possible to create an option of unit 256 repetitions and have it flattened so that handling it would be as simple as handling a U8? Well, it depends on what you mean by handling, because from the code perspective, it's still just an option, etc. of unit. But yes, it will compile down to a single byte. So yes, it is possible. It's just a corner case that I wouldn't expect to see in a while, but yes, it is possible, and it is possible just in the current Rust versions, or so I think, at least. Maybe 255 repetitions, unless it would crack the compiler considering the level of nesting, but that's another thing, really. Cybertraber from Twitch asks, are phantom types strictly necessary, or could everything also represented with unit variants? Well, phantom types are also an interesting topic. It's indeed a little bit connected to what I've told you about. As far as I know, the language rules for pointers, so what kind of pointer is a subtype of another pointer, do permit using pointers to unit or unit variants as a sort of phantom type, and I did see that in the wild actually, but you know, I always considered phantom type to be more of an abstract convention. But yes, of course, if what you mean is that it could be used like that, yes, I think it could be used like that. And I've actually did use unit type in very, I'd say, weird ways. So, for instance, you could use the unit type to just create some fields that are available or not, depending on what kind of generic arguments you have the type instantiated with. So, for example, you have some field x, but only if the type is instantiated with integer or something like that. And it can actually be quite useful if you make a library for multi-dimensional computations. It's not an easy task to choose the best answer, the best question, sorry. I personally like .chris please question for option of non-zero U8, considering that that's exactly the way I thought while reading about this topic. So congratulations, .chris. The book is yours. Enjoyed my presentation. Have a good day.